So this is a webinar that I'm going to be presenting about common SolidWorks simulation issues and hang-ups that people tend to have. As I said earlier, my name is Andrew Potter. I'm a CSWP certified SolidWorks professional in the SIM category, and I've been working here at MCAD for a little while, and I'm just going to talk to you about some things that we've seen, things to make your sims easier, eliminate some headaches in your process. So we're going to have a couple things we're going to talk about today. On our agenda, we're going to talk about thin-walled components. We're going to talk about how boundary conditions affect what we're doing. We're going to talk about how body simplification is important. We're going to talk about face splitting and how it's useful when we want to apply loads in a very specific manner. And then we're going to talk about contacts and why specifying contacts is important. So first up, we're going to talk, as I said, thin-walled components. One thing I see a lot is that there's a lot of confusion about where the line for shell elements versus solid elements when you're trying to model a part. As you can see, we've got sort of a continuum here, and on the left we've got our elements with a low aspect ratio, something that's nice and square. All the proportions are equal to each other. There's not any slenderness ratio, so to speak. But you can see as the aspect ratio begins to narrow and become high, compared our length to our thickness becomes an appreciable amount. So now we need to start looking at whether shells would be appropriate. And you can see there's this sort of gray area in the in-between. And that's where it really becomes necessary to look at what the model is and see if a shell can help you out. One example here is I have a half of a pulley that I've taken and extracted a mid-surface from. It's a really easy process. It's really easy to do. It starts with you just go to the mid-surface tool under your surfaces, and as you can see, we've got this update pair button, and if you click that, it'll automatically go and recognize these face pairs and color them purple and blue, find our surfaces, and then we can create our mid-surface, and it'll pop out a surface that looks like this. It's a nice middle of the line, the neutral axis of where our shell would be defined. So if we go forward on it, when I mesh these two parts, right, one out of solid mesh and one out of a shell mesh, when I use the solid mesh, it takes almost, just near as makes no difference, 200,000 elements. That's a pretty sizable chunk of computational domain. Same 1.1 millimeter element sizes done on a shell, I come out at a nice handy 27,000 elements. That's a pretty big difference, order of magnitude, in the shell or in the mesh sizes. And you can see that even on the simple part, it took 11 seconds to mesh this part with enough elements to get 2 elements through the thickness for a thin-walled part, whereas my shell was completed in 3 seconds flat. So it's pretty easy to see that the shell element is going to save you considerable computational overhead and make sure that you are able to solve your meshes in a feasible amount of time. And you can see over there my results as far as the displacements are basically near as makes no difference the same. We have one that's 0.301 millimeters and the other that's 0.318 millimeters. So effectively the same displacements. Moving on, we're going to look at boundary conditions. One of the things that really matter about boundaries is when people get willy-nilly and just go in here and grab the standard fixture and fix absolutely everything and bind it all down. Well, the unfortunate thing about fixtures is that when you really use a fixture and you tell it that somewhere is fixed, you're actually telling it that that spot cannot deform and cannot move in any way, zero deformation. And in reality, some things aren't a true rigid connection like that. There's a little bit of deformation, but not to the same degree. So we can come in and start using things like reference geometry to specifically constrain the degrees of freedom that we want without having to come in and just use fixtures everywhere. So you can see on this one, I've grabbed the edges where it defined my shell for that guy. And instead of just using a symmetry or something like that, I've bound it against the right plane, told it it couldn't move away from it, just like if the other half of the shell was there. And I've told it it can't rotate about the first two planar directions, but it can rotate around the interior or normal plane direction because of the deformations that will be happening. So in this one, you can see how I was able to make this, this boundary condition without restraining all of the degrees of freedom and getting weird edge effects and fixture irregularities and stress concentrations. Instead, I can end up with a nice model that doesn't need a complex set of fixtures. Another thing I see a lot on boundaries is the difference between selecting a face and selecting the actual body. I see this one a lot with surface temperature. People want to do a study where a part has been heated and they want to know what kind of thermal stresses they're going to see in the part. Normally, their first instinct, they see temperature, they see this button here that says select all exposed faces, and they're like, yeah, that's what I totally want, and they click that. The problem is there's a menu back in SolidWorks that has the 0 strain reference temperature. So for this case, the default is set to 25C. So in this we have a 275C difference between the 0 strain and the temperature we've imposed. That's caused right here us to have this weird boundary condition where right at the surface it's trying to make the temperature do a huge discontinuity jump from 25 up to our 300C, right at the surface and nowhere else. And you can see how that's led our part to have this really weird sort of banana-shaped, crumpled, corn-on-the-cob look. And the mesh that I use is painfully apparent because it's stretching around each one of the nodes and not correctly showing what we want to see. Notice how instead, on the bottom one, instead of grabbing all these faces, I just grab the body, boss extrude one, this big bar that I have here, and impose the same temperature limit. Nothing else between our studies changed except the way that I put that body in there. And you can see here now it's thermally expanded really nicely. It's grown in length, exactly what we were looking for, a nice 0.34 millimeters, as opposed to this corn-on-the-cob thing we had going on up there. So that's one of the really big ones for a surface condition as far as boundaries, and you can see how they will really drastically change your simulation if you don't do the correct one. Moving on, we're going to look at body simplification and how to simplify your bodies to make them easier to solve and avoiding unnecessary geometry. So you can see on here that this pulley that I have has two configurations. It's got the default and it's got what I've called the configuration of the finite element analysis one, the sim configuration. And in the default one, it's fully featured. It's got, laser etching on the outside of the face. It's got all the manufacturer info. It's got really, really fine minor notching right there. All these tiny, crazy little meshed features tiny little features that you would have a nightmare trying to mesh, but don't actually contribute to the structural integrity of the part. For example, especially the laser etching or very slightly inset embossed text. If you tried to mesh that, it would have a nightmare of a time trying to squeeze elements in to like the thinness of a laser etched word. But another one that you see is a lot is fillets, because the mesh is much easier for the software to define across orthogonal or planar surfaces. When you have a rounded surface, fillets and rounds, you end up having the computer having to do extra meshing work around those fillets. So if you have cosmetic fillets that are only there to make the model look nicer and make it more appealing as like a drawing, you can easily just suppress those for the simulation, save yourself a massive headache on the features with no loss of resolution or accuracy to your studies, especially with things like tiny little holes. Like if you had a large long beam and there was just a small little hole right in the middle, like it's 2 feet long, and there's a 1/16 of an inch hole somewhere in the middle. Well, it's going to break its back trying to mesh that little hole, and you don't need it. It's not important to the sim unless you are actually working with that one little 1/16 inch hole. Other than that, you don't really need it there. So That's another thing to get rid of. Extra parts, what I mean by that is if you have a multi-part assembly, but you're really only trying to get the stress state down in one of the parts of the body, don't put the extra parts of the assembly in there. Instead, cut them out and use a fixture that is a representation of the rest of the body there. So an immovable, no translation, a fixture, something to give you how it would relate to the body above it. And you can sim the same loads and such, but don't need all of the extra contacts and no penetrations and all those other things that would normally need to be solved for. Finally, one thing to really keep in mind is that symmetry is of utmost importance when you're doing these modeling challenges. Any time that you can cut the model into a symmetric piece, you've made your computational domain half as big right off the bat. And that's so you can have double the mesh for the same part and get a much finer detail for the same solve time. And it's nice to note that if you have more than one plane of symmetry, you can use all of those planes of symmetry. So if you had a part that was symmetrical across the front, right, and top plane, you can theoretically divide it into a 1/8 of the original part using symmetry constraints and solve that one little chunk to save yourself a lot of modeling effort and a lot of meshing headache. You know, especially if there was a lot of contacts, doing 1/8 of the contacts is totally worth it if you're trying to save time and get your model done at the same accuracy. Moving on, we're going to talk a little bit about face splitting. You can see on my pulley that we've added these split lines, right? This is a really simple case to allow us to put the pressure load right where it's actually happening. I see a lot of times that people will put a force, they're saying it's acting on the end of this beam, and they'll either apply it directly to the edge, like right on the split line, and that's not accurate because it's really hard to have a stress right across a line. So instead you can make like an imprint of where the force would have been applied by using the split lines and sketches to apply those loads more realistically to the way that they would be done on the body. On that note, you can also use these split lines for, say, let's say you had an assembly that was bolted together and due to the limitations of the geometry, the virtual connectors won't work. You could actually use the split lines to define where the heads of the bolts would contact and cause pressure on both sides of the plates and effectively at least try to model those kind of pressures accurately on both the top and bottom surfaces. Another use for them is for when you want to get results from only a certain point or you want to fix something in only a certain point. Obviously, if you have a face and it was, spot welded on a couple places to somewhere else, you don't want to fix the whole back face. You want to fix just those spot welds that fixed it to the face so that the simulation will be more accurate. And you can do those by making the little circles on the back to simulate where the 4 spot welds would be and then use that instead. So that's just a way to make your sims much more accurate and avoid the headaches of seeing unrealistic results when you just sort of generally apply a force. Finally, this is a big one, contacts. I know setting up the bonded, no penetration, allow penetration, all of that can be a little daunting sometimes. But what's important is that previous thing I talked about with split lines, we can use that to make our simulations much faster when it comes to contact. If you see over here, we've got this hose clamp, and I'm going to apply pressure to it to cause those two faces to come together. And so I'm telling them that they're going to have a no penetration contact that won't allow those two faces to come through to each other. I could have selected the entire length of both of those faces, but then when the software went in, it would have to calculate all of that. I'll show you what I mean. When you look at contact solutions, node-to-node contact is the standard way that you see a lot of no penetration contacts done. Node-to-node is only for touching faces because it takes a node, it glues it to the other node, and says that these things, or not glues, but relates that to that node and says these nodes can't penetrate through each other and relates each one of these sections of nodes on a compatible mesh. That's the important thing to take away there, that the node-to-node can be done on compatible meshes. When we move away from that, however, we can do node to surface. where you can see here there's a node projecting its lines down towards the area of the surface or component 2. And the way it does the contact on this is it checks to see whether this node on the surface has come into contact anywhere on the small area of the target. And by monitoring these distances, when one of them goes to 0, the solver knows the contact is there. But it always is updating these contact constraints and seeing if these parts are touching constantly. So if you decide to make the surfaces the entire length as no penetration, you'll find that the solver is going to continually ask that entire length of nodes and elements whether they're in contact all the time. That's just wasted computational overhead that you don't need to spend while waiting for your solver to finish. It's important to note then that the node to surface can be a non-touching start, because on this it's calculating a distance. So for my previous example with the self-contact, we would use the node to surface because we want them to calculate that. But then you can go one step further, and in the SolidWorks menu there's the even more accurate form of contact, which I don't have a picture here for you, but it's surface to surface, where it literally engages the equation, parametric equation that defines this surface, comes up with the XY coordinates of what that surface is, and then takes the other surface and sets them equal to each other and analyzes at the current geometry, is there anywhere that these faces have a coincidence or an intersection, and then it defines the contact. But asking a computer to constantly compare two very large and gross parametric equations obviously results in a pretty diminished capacity to solve quickly. Instead, you end up with lots of wasted computational effort looking at if surfaces are ever going to touch when you as the designer should have from the start known they weren't going to, so you don't tell them that they're going to, and you'll save tons of computational time. That's sort of it for the active presentation portion of it. But what I was hoping is that anyone who had questions could have them answered here, and I can also, if any come up after this, we can be reached at the MCAD tech support at support@mcad.com or at our phone number. And then obviously I as well can be reached at apotter@mcad.com if you have any further questions about anything here. So if anyone has any questions or would like to ask a question, make a statement, anything, I'm going to open it up. I'm not seeing any hands getting raised, so I think if that is the case, I will say that it's been a pleasure to present to you guys, and hopefully this helped clear up some issues about, or clear up some situations in simulation where you can make use of different solutions for it and improve your workflow and improve the quality of your sims. So with that, if nobody has any other questions, I think I'm going to call the webinar now. And as I said, thank you for watching.